Hey, welcome back for AP Chemistry. You're here with Mrs. Mays, and today we're going to work on writing the equilibrium constant expression. Since this is our first podcast about equilibrium, let's talk about what it is. Basically, chemical equilibrium describes a condition in which the concentration of the reactants and the products stop changing. So you're not decreasing reactants nor increasing products, you just see sort of the flat line on the graph. This occurs when opposing reactions are proceeding at equal rates. And it necessarily requires a closed chemical system because if it's open, then some of your products could escape or your reactants. So you have to keep it all contained. So here's an example of a reaction. The formation of water by combining hydrogen and oxygen gas. So if we're going forward, we call this the forward reaction where the reactants are producing products. There's also such a thing as the reverse reaction where we would have the water turning back into the elements from which it is formed. And if we write a double arrow like this, then that's what we use to indicate a reaction that is reversible. Some reactions will go in the reverse direction as soon as there's enough product to have effective collisions. So we talk about reaction rates just as we did in kinetics. So the rate constants are given for various reactions to determine when is the system at equilibrium. Remember in our graph, in the simulation we did in class, we had the concentration of reactants going down, and the concentration of products was going up. But over time, they sort of leveled off and didn't change anymore, and we didn't see any more increase or decrease in either one. So this portion of the graph here is the kinetics portion where we can calculate the slope. And then we can determine the half-life and the rate constant and all that great stuff. But this side of the graph, once it levels off, this is when the system is finally at equilibrium and the concentrations don't change anymore. So this is the equilibrium portion of our graph when we're monitoring the change in the concentration over time. So given a reaction where A turns into B, the forward reaction would have a rate constant of K for the forward reaction that depends on how much of A is present. The reverse reaction depends on how much product is there, because now we're turning the products back into the reactants. So we use a different rate constant, Kr, because the activation energy is different in the forward direction than it is in the reverse direction. For gases, I need you to recall that concentration is proportional to quantities determined by the gas law, PV equals nRT. This is our ideal gas law. I'm going to solve for molar concentration by rearranging this. I know that the molarity is moles per liter. In other words, that's my N divided by my V, right? So let's substitute those quantities into the ideal gas law. And that gives us that the molarity will be equal to the pressure divided by the gas constant R. That's the gas constant for R is the one we use with atmospheres, 0.0821, right? Oops. And not the one we use for joules. And the temperature is, of course, in kelvins. Be careful about your units. So then the pressure of substance A would be the partial pressure that's created only by substance A, and we can calculate the molarity of that substance if we know its pressure. We can do the same for substance B. We can calculate its molar concentration based on its partial pressure. So the forward rate, so I've just taken my rate law and substituted in the place of the concentration of A, we've substituted what we said it's equal to the partial pressure of A divided by R times T. The same would be true for the reverse rate, only this time we need the partial pressure of B to get that molar concentration of substance B. So we can solve the rates using concentrations or using pressures if we're dealing with a reaction in the gas phase. At equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction because we're no longer having a change in the concentration over time. So this is where equilibrium constants come from. KEQ is called an equilibrium constant, and by constant we mean that this value doesn't change when it's at the same temperature. If the temperature increases, then we know the rate increases, and the rate increase makes the equilibrium shift. So temperature is the only thing that can affect the equilibrium constant. We use Kp for reactions that are in the gas phase because we use pressure. Kc is used for aqueous solutions. Did I spell that right? Looks good. Okay, for aqueous solutions because Kc refers to concentration, Kp refers to pressure of gases. And I'm going to be picky about you using the right one. The law of mass action is expressing the ratio of product molarities to reactant molarities, where each of those molarities at equilibrium, and only when they're at equilibrium, would be raised to the corresponding powers by the number of moles of that substance. I know that sounds confusing at first, but it's not so bad. Let me show you how it works. If we have reaction where A plus B makes C plus D, then this is my coefficient. How many A's, how many B's, how many C's, and how many D's. For my equilibrium constant, I'm going to put my products on the top, products over reactants. So the concentration of substance C is raised to the power of however many moles there are in that balanced equation. And substance D has its concentration raised to the power of however many moles there are in the balanced equation for substance D. Now we put products over reactants, so I have to put my reactants on the bottom, substance A raised to the power of A, and substance B, concentration, moles per liter, raised to the power of little b. Whatever these numbers are, they go into the expression. Oh, look, I already wrote it. How fun. So here's an example if we have like real things, not A, B, C, D, but real things like hydrogen and iodine forming hydrogen iodide. So I write my equilibrium expression, KEQ, is equal to the concentration of the products raised to the second power, right, because it's got a 2 in front of it, divided by the concentration of my reactants. Hydrogen gas is not going to be raised to anything but 1, and I don't have to write that in. Iodine also just has a power of 1 because there's nothing in front of it in my balanced equation. So that's what the equilibrium expression looks like, the products over the reactants. If your equilibrium constant is greater than 1, that means that the products are favored because you would be dealing with a fraction where the numerator is larger than the denominator. On the other hand, if K is an expression that is less than 1, if it's a value less than 1, then your reactants are favored because in that situation, your denominator is larger than your numerator, and that would give you a value for the equilibrium constant that is lower than 1. When K is much greater than 1, we say the equilibrium lies to the right. And on the other hand, if it's much, much less than 1, we say that the equilibrium lies to the left because it would favor whatever's on the left side of the equation more than what's on the right side of your chemical equation.
For example, if we're given the reaction of oxygen plus sulfur dioxide, then notice all of these are gases, so when I write this equilibrium expression, we're going to call it Kp. And in my Kp expression, I will put the pressure of the products, that would be sulfur trioxide, raised to the power of the coefficient in the balanced equation. So that would be to the second power divided by the product of the pressures of my reactants raised to the powers of their coefficients. So oxygen has a coefficient of 1, right? So I don't have to write that one in. But the sulfur dioxide is going to be raised to the second power. So let me put the pressure of sulfur dioxide raised to the second power. So notice that with Kp, I use parentheses, P for parentheses, because I'm using pressures. I use square brackets, though, for concentrations. These are all gases, and I can express the concentration of gas in moles per liter. That is possible. But since I'm given gases here, I'm going to write a Kp again. So we'll take the pressure of the products, NO2 and O2. That goes on top. And then the pressure of the reactants goes on the bottom. So I have NO and O3. This is one of those reactions that describes how nitrogen monoxide can destroy the ozone layer, and that reaction is pretty devastating for us. In example 3, the equilibrium expression would have the pressure of oxygen raised to the third power divided by the pressure of ozone raised to the second power. So there's the Kp expression. If we were writing a Kc, suppose that in our problem we were given molarities, then we would have to put the molar concentration of oxygen over the molar concentration of ozone. Pay attention to your problem and the values that you're given. If you're given molar concentrations, use brackets. If you're given atmospheres or kilopascals, then we'll be using pressures. So just pay attention to your problem.
If I were to reverse the reaction, then the equilibrium constant would simply be the reciprocal of the forward reaction. Because then I take what was the products that we put on top and I turn it around. If I'm going backwards now, then these are the products. So they go on top. So we just flip it upside down. Your fraction gets inverted. So my reaction, my equilibrium expression was C to the C and D to the D. But if I turn it around and go backwards, then my KEQ for the reverse reaction is going to be A raised to the A, B raised to the B, C raised to the C, and D raised to the power of D. Let's put numbers in. It'll make more sense with numbers. So here's a reaction where dinitrogen tetroxide decomposes into 2 molecules of nitrogen dioxide gas. So in the forward reaction, going this way, my value at equilibrium is 6.46. So to determine the equilibrium constant in the reverse reaction, I'm going to take my KEQ for the forward reaction and raise it to the power of -1, which is the same thing basically as taking the reciprocal of that fraction, right? So let me get my calculator and find the inverse of 6.46. So we type in 6.46 and then push the button here that's x to the -1, enter, and I get 0.15479. So for the reverse reaction, let me clear that out of the way. When we turn our products back into the reactants, I indeed have an equilibrium constant of 0.155. And it's different because the activation energy going forward is not the same as the activation energy going in reverse. The hill may be higher to climb if it's exothermic, or it might be a shorter hill to climb if it's endothermic reaction. So here's some tips and tricks and shortcuts. The KEQ we just covered is the reciprocal when it's reversed. And if you have a reaction that has been multiplied by a number, like we sometimes do in Hess's law or in complex redox, then that number in the equilibrium expression will be raised to the power of that number, because our coefficients, remember where we had A moles of substance A, we wrote it with A raised to the power of A. Well, if I multiply this by 2, then I have to multiply by 2 up here as well. So it's raised to the power of that number, not just multiplying by the number like we did in enthalpy. Now, if the equilibrium is a net reaction made up of more than one steps, then what we have to do with the value of K is multiply the equilibrium constants together, not add. We add for Hess's law, we multiply for equilibrium. When the substances in the reaction are all in the same phase, we call it a homogeneous equilibrium. But of course, a heterogeneous equilibrium refers to having different phases, like you may have some things that are liquids and some things are gases, and why can't I spell different? There you go. Or you may have some solids. So if you do have solids, then it's important to understand that we don't have a place for those in the equilibrium expression. We're not going to write KEQ with our solid reactant in the denominator, because how do you calculate the concentration of a solid? It's not dissolved in anything. You can't do moles per liter. It's just all like one big chunk of stuff. It doesn't have a concentration. So what we do is we leave out anything that are solids and liquids. We just don't include them in the equilibrium expression at all, because it doesn't make sense to do so. So pure solids and pure liquids are not included in the expression, because really their concentration is considered to be like 1. It's just all that same stuff all the way through. And so if you put a 1 in the denominator here, you're not really changing anything. So we get to leave that out. So when we're looking at equilibrium constant expressions, remember, we use partial pressures of gases that we calculate. Partial pressures of gases are used to calculate the Kp expression. So if you're putting pressure into the K expression, you have to call it Kp. But if you are using molar concentrations in your equilibrium expression, then you call it Kc, not Kp. They are not the same. You have to be careful. And if you have pure solids or pure liquids, we do not include them in the expression. To determine KEQ, this is super important, you must utilize conditions at equilibrium. Not any old value will do. You have to only use the values that will be established at equilibrium. The only thing that changes your equilibrium values would be temperature, and nothing else ever. Temperature is the only thing that can cause your equilibrium to change. And that's going to be important, because I'm going to ask you questions about this in class and on your tests about how do I change the equilibrium constant? And you better know that the K stands for constant, right? Constant. Sure, that's how we spell constant. Here's one other important thing. The Kp can be converted into a Kc, but we have to use the relationship from the ideal gas law. We'll take our equilibrium for molar concentration times R, the gas constant, times temperature in kelvins, raised to the power of your change in the number of moles of gas. Not moles of anything else, only gases, so that we can calculate Kp based on the partial pressures of whatever gases are involved. So we can turn one into the other, but we cannot use one expression in the place of the other because they're not exactly the same.
Now in our final example, let's convert the equilibrium expressions according to the equation we just saw. So first, I'm given pressure in atmospheres. So let's go back to the Kp that we calculated with pressures. So the pressure of sulfur trioxide is squared, and the pressure of oxygen is not squared, but the pressure of sulfur dioxide is squared. How come I keep forgetting to write the pressure in there? There we go. So now let's take the values from our equation. Now let's take the values that we're given in the problem and substitute them into the equation. So I take the pressure in atmospheres of sulfur trioxide and square that, divided by the pressure of oxygen, not squared, 0.045, and the pressure of sulfur dioxide, 0.075, no, not 0.75, scoot that over, but we will square that value. Now, in the K for kinetics, we must have units, but for the capital K in equilibrium, we don't use units at all. It doesn't make sense to do so. Now we'll calculate the value of Kp. So I need my calculator. Okay, so I have 2.5 squared divided by parentheses 0.045, not squared, but I'm going to multiply that by 0.75, that is squared, and then close off my parentheses to enclose the denominator. There we go, 246.9. 246.9, we could just call that, how many sig figs do we get? 2 sig figs. So 250 is my equilibrium expression for Kp. And we can convert this into a Kc value by applying the equation we had before. Kp equals Kc times RT delta N. So first I want to know, what is delta N? Delta N is going to be the number of moles of gas in the product, which is 2 moles, minus the number of moles of gas that we had in the reactants. And that was 3 moles, 2 from SO2 and 1 from O2. So delta N is a -1 in this case. All right, so I'm going to have Kp divided by R times T, 0.0821, times the temperature in kelvins. So we had 25 degrees Celsius, so that's 298 kelvins. And this part, the denominator, has to be raised to the value of -1, or the value of delta N. So let's get our calculator out and do this math. So I'll take my answer and divide that by, let's get some parentheses around the denominator, 0.0821 times 298 kelvins, and that quantity is raised to the value of -1. So I'll enclose the entire denominator inside the parentheses and make sure that my -1 exponent applies to the right spot. And I end up with a Kc value, 6040.9. So we could call that, well, we'll just call it 6040. And you can apply that same equation to turn any Kp into a Kc. It's a variation on the ideal gas law that we use for equilibrium problems. That's the end of the first podcast about equilibrium expressions. Next time we'll be talking about the reaction quotient. So we'll practice in class, and I'll see you guys soon.